In this session, we will discuss VV connection, or it is also called as open delta connection. Start with the open delta or VV connection. If one of the transformer of delta system is damaged, or there is a fault, or it is opened, then still the system will continue to supply three-phase power. If this defective or faulty transformer is disconnected and removed, the remaining two transformers continue to function as a three-phase bank with rating reduced to 50% of the total delta bank. That is, if it is the three transformer which is connected in delta, if it is supposed to supply 100% the volt ampere to the load, then if any one of the transformer is the opened or faulty or it is removed, then the capacity of the two transformer which is capable of still supplying 50% 58% of the load. This connection is known as what we are calling as the open delta or PV connection. Thus, in the open delta system, the two instead of three single phase transformers are used for three phase operation. Still, it is one transformer is less in the open delta, then it is capable of handling a three phase operation. Now we will compare the delta connection with the open delta connection. Start with the delta connection. I want both the primary and secondary here, the delta connection. Then the current in each phase, that is what I am representing here is, that is IA, IB and the IC. Then each phase current is equal to what I am taking here is I. Then the line current in the case of delta is root 3 times the phase current. Where the line current in phase A, B and C are I1, I2 and I3. These I1, I2, I3 are root 3 times phase current, that is equal to I. Then the line voltage, which is same as the phase voltage in the case of the delta connection, between AB and BC and CA is all are the equal. Therefore, I am representing here the voltage between A and B is V, between B and C is also V, between C and A is also the voltage V. Then what is the output volt ampere from the three phase system? That also we know. That is the output volt ampere output is root 3 times line voltage into line current. We'll come back to that. That is, we know that the phase current in the secondary. We are interested in what is the power delivered by the volt ampere delivered by the secondary we want. Therefore, the phase current, that is phase current is current in each phase, is equal to IA is equal to IB is equal to IC. Therefore, all the magnitudes are same. It is a balanced system what I am considering. Therefore, that is IA, IB and IC is equal to, that is what I am calling as I. Whereas the line current is represented by IL, that is equal to root 3 times the phase current, that is what I am getting is root 3 times I. That is I is the phase current. Then, but in the case of the delta connection, both line voltage and phase voltage are same, that is represented by V. Therefore, in the closed delta or delta connection, load volt ampere is given by, it is a root 3 times line voltage multiplied by line current. What is the line voltage? Line voltage is V, line current is root 3 times I. Therefore, what I am doing is root 3 V into root 3 times the same thing, line current and line voltage I am substituting in this equation. Therefore, what I am getting is 3 times Vi is the output of the delta connected the transformer. Now, I am considering the open delta now, that is one of the transformer is removed from the closed delta, that is I am drawn here the secondary, and the current in the each phase is IA. Then you can see here it is IC and IA. Then the total which is current which is flowing here, you can observe in the previous it is root 3 times I. Here the line current is the same as the phase current. Line current is same as the phase current in the open delta. Okay, that I am demonstrating here. I am drawing here the primary of the open delta. Now I want to calculate what is the load volt ampere in the open delta. Okay, the open delta KVA, it is once again it is root 3 line voltage multiplied by line current, because it is act as a three phase system still. Therefore, in the case of the line voltage, you can see here the line voltage remains same, V and V. Then the current which is the line current, previously it is root 3 times I, now it is only I. Therefore, in the line current what I am substituting here is I. Previously for the closed delta I substituted for line current is equal to root 3 times I, whereas in the open delta the line current is same as its phase current, therefore it is I. Therefore, the total volt ampere of a open delta what I am getting here is root 3 times V into I. Then if you are taking volt ampere of the open delta to volt ampere of the closed or delta delta connection volt amperes, that is open delta volt ampere, that is root 3 times Vi, divided closed delta volt ampere, that is 3 times Vi, then what I am getting is 0.577. Suppose if you want open delta load volt ampere, open delta volt ampere, it is 0.577 times closed delta volt ampere, means the open delta is capable of delivering a load of around 57.7% or precisely, and if it is taking approximately it is 58%. That is the load that can be carried out by the open delta bank is 57.7% of the delta bank. Means that is still if the one of the transformer is not operating in the closed delta, then still it is capable of delivering a three-phase power with reduced capacity. Then we have to look into the voltage relation in the open delta. That is, it is a primary and a secondary of the open delta. The voltage which is across AB, that is VAB, VBC and VCA is the line voltages. Similarly, in the primary, that is caps VAB, VBC and VCA are the line voltages in the primary side. That we will look into the voltage relation here. That is VAB, VBC, VCA are the line voltages of the primary side, whereas smaller VAB, VBC, VCA are the voltages in the secondary side. Then we know that in the closed path, the sum of all the three voltages VAB, VBC plus VCA must be is equal to 0. It is the characteristics of the three-phase system. Then at the same time, from this relation, VCA can be calculated as minus of VAB plus VBC. That is, we are transferring these two terms to the right hand side. Then I am expressing the primary VAB, that is the line voltage, as in terms of its phase voltage. That is, you can see here, that is VAB is equal to VLP an angle of 0 degree. That is nothing but VLP is primary line voltage. What I am writing is VLP, because the magnitude of VAB, VBC, VCA are equal, but their phase displacement is 120 degree. Then VAB is taken as a reference. When the magnitude is remains same, the one magnitude I am representing as a line voltage of the primary, that is VLP an angle of 0 degree. Similarly, VBC, that is next phase voltage between B and C, is having the same magnitude, but it is lagging an angle of 120 degree. Then similarly, the third line voltage VCA is having the same magnitude but lagging by 240 degree with respect to VAB. Then coming to the secondary side of the transformer, that is VAB is VLS an angle of 0 degree. That is VLS as the nothing but it is also represented by a secondary line voltage. VAB is, that is VAB, VBC and VCA are the line voltages. Their magnitudes are equal but their phase displacement is 120 degree. Therefore, first I am taking VAB is VLS, that is the line voltage and angle of 0 degree. Then VBC is VLS and angle of minus 120, and we know that VCA I am calculated here. That is VCA is equal to minus of VAB plus VBC. So the same thing I am writing here. Then we know that the magnitude of VAB and VBC are same as the line voltage, but with their phasor relation you can put it. It is VLS and angle 0 degree. It is a VLS of an angle minus 20 degree. Therefore, if you are solving this vectorially, then what we are getting is VLS an angle of 120 or it is minus 240 degree. Means that is the third voltage, that is the voltage between C and A is VLS an angle of 120 or minus 240. Therefore, we come to conclusion that it is seen that VCA is equal in magnitude to the secondary transformer voltage and 120 degree apart, and thus balanced three-phase line voltage applied to the delta because in the primary we are applying the balanced voltage three-phase voltage, then even though it is open delta, in that case we are getting the balanced three-phase the voltage across the secondary of the open delta. That is what I mean. Then some of the important points worthwhile to note for the open delta systems are, that is where exactly we need this open delta. Initially, if our load is very small, a three-phase load is very small, instead of investing on the transformers, then we have to invest only on the two transformers, expecting that there is an increase in the load. Then using only two transformers, you are capable of handling your lower loads. That is the one first advantage. The three-phase load is comparatively small previously, so that installation does not warrant a third transformer bank, and so that you can make it an economy. One of the transformer in the delta bank fails, so that service may be still maintained with the reduced capacity. That is another advantage. Then with reference to the first point, subsequently load is increased, already two transformers are there, then you have to add one more transformer so that you can capable of delivering the extra load. That is, it is anticipated that the future load will increase to warrant or need the closing the open delta at some later stage. That is, adding one more the transformer can increase the capability of the three-phase system. And main disadvantage of this particular open delta is that is the secondary terminals tend to become unbalanced to a greater extent when the load on the system goes on the increasing. This is about the delta connection, open delta connection.